In this video, we present our work on robust method for removing dynamic objects from point clouds. The goal of this work is to build long-term mapping solution for autonomous driving purposes for urban structured environments. Point cloud maps are built from data collected by driving a mobile mapping system on roads filled with dynamic objects. So it is important to remove these dynamic objects as they can lead to ghosting effect as seen on the video snippet. In this paper, we propose a new approach to remove dynamic objects from point cloud maps by using a combination of object detection methods and occupancy maps. A good amount of work has been done on detecting and removing dynamic objects in laser scans, and different methods have been proposed to solve this problem. These methods can be classified into three categories: model-free approach, neural network-based approach, and finally map-based approaches. Each of these categories, though, have drawbacks for autonomous driving use cases. For example, the neural network-based approach is only capable of detecting the category of objects it was trained on, while the map-based approach is very sensitive to allow quick update of occupancy maps. To address the above problems, we propose a new occupancy probability update strategy by maintaining occupancy history of voxels. We have a method to integrate object detection algorithms to accelerate the process of building occupancy maps. Lastly, we introduce a method to generate artificial endpoints using virtual sphere to extract as much occupancy information as possible from input data. Again, we use a combination of model-based and occupancy map-based approaches to ensure that the occupancy probability update function favors long-term occupancy states.
We now present our algorithm in detail. We use Octomap for building occupancy maps, but we have modified it to favor representation of long-term occupancy states or quick updatability of voxels. Our algorithm pipeline looks as follows. It starts with a registered set of input point cloud from a LiDAR. We remove the points which are beyond distance r from the sensor origin to remove noisy data. Next, we use object plane detection algorithm to identify the ground points and the corresponding ground voxels. After that, we use object detection to classify the remaining non-ground points into object and non-object points. After classifying the points, we perform voxel traversal to update the occupancy scores of the voxels. Finally, at the end of this process, we get the occupancy map. We overlay the occupancy map on a set of new input point cloud data and remove the points which fall in the free space of occupancy map. One of the shortcomings of using voxel traversal in building occupancy map is that it causes holes in the occupancy voxel representation. This happens when the rays are incident on flat surfaces at very shallow angles. It can be seen in the image on the top, where the laser ray cuts through several surface voxels, decreasing their occupancy score before stopping at the voxel containing the endpoint. This effect is very clearly evident on the ground plane. To tackle this problem, we use ground plane detection to identify the ground voxels and add them to a set. We also maintain a counter per ground voxel to filter out the false positives. So when performing occupancy update using voxel traversal, we check if the voxel being updated is part of the ground voxel. If yes, we don't decrease the occupancy score of this voxel. In object classification stage, we detect objects using deep learning-based object detection method. Next, we extract the frames which consist of moving objects and classify the object points inside the bounding boxes as object points and outside as non-object points. We perform voxel traversal from the sensor origin to the object points and decrease the occupancy score of all the voxels along the path of the rays to the object points, including the voxels containing the endpoints, as we already know from object detection that the points belong to a moving object. For non-object points, we follow the same process, but we increase the occupancy score of the endpoint voxels. To achieve slow update of occupancy map, we maintain free counter value per voxel. The free counter value indicates the number of times the voxel has been measured free. It is incremented by 1 every time the voxel is measured as free and decremented by 1 when it is measured as occupied. The lower threshold for free counter value is set to 0. We represent the occupancy score of the voxels using log odds. For the voxels which have free counter value of 0, we use equation 1 on the right to update the occupancy log odds score of the voxel. For the voxels with free counter value greater than 1, we use equation 2 on the right. where we divide the measurement update by free counter value to slow down the measurement update. The intent behind this is to make it hard to increase the occupancy probability of voxel, which has been measured free previously. To understand how this works, consider the image on the right. Here, the area bounded in the red has been measured free multiple times in the past, and the voxel present in this area have high free counter value. Now, in the input data, this area has been occupied with some vehicles. In this case, we use equation 1. If we use equation 1, we would quickly increase the occupancy score of these voxels and end up marking them as occupied, which is not what we want because the previous measurements, we know that this space is mostly free. Using equation 2 will help slowing down the occupancy update of these voxels. Next, we introduce the concept of virtual endpoints. The endpoints which are far from the LiDAR are often noisy. So when mapping an outdoor space, it is useful to trim the input point cloud. However, by removing these points, we lose valuable occupancy information of the surrounding. For example, the endpoints which lie in the blue rectangle are far from sensor but contain useful occupancy information. To solve this problem, we project the endpoints with distance greater than r onto a virtual sphere, which is also of radius r and centered at sensor origin. Next, we perform voxel traversal for the projected endpoints and decrease the occupancy probability of all the voxels along the rays from sensor to the endpoints, including the voxel corresponding to the endpoint. Finally, we superimpose the fully built occupancy map on point cloud map and remove the points which fall in the free space of the occupancy map.
In order to evaluate our algorithm performance, test and real-world experiments were performed on NEO dataset and Kitty dataset. Our approach of removing dynamic object points from point cloud relies on building occupancy maps. It's hard to estimate the time invariant occupancy state of an environment with a single set of scans of the area, as scans may contain moving objects. Therefore, we need multiple sets of scans collected from the same area to identify temporarily static objects. To the best of our knowledge, Kitty dataset only has a few loops of driving through the same parts of the map, mostly for loop closure. So we built our own dataset in urban area around NEO office. Our vehicle with sensor setup is shown on the right image. We chose a voxel size of 30 centimeter empirically to cover a larger area for the map. The results for us included multiple loops of data which gave us good recall values. Though false positives caused by holes in flat walls and ground reduced our precision scores. An object detection algorithm misclassification also added to false positives. Here we show a video snippet of new dataset collected around the office. The left window shows the input point cloud scans with dynamic objects, and on the right are scans without dynamic objects, after applying proposed algorithm. The video very clearly shows ghosting effect on the left for moving objects, while our method is able to detect the dynamic objects and remove it successfully on the right. We use precision and recall values to evaluate performances. The scene is at an intersection where a lot of stop cars can be seen on the left and the ghosting effect when the ego car starts moving. Next up, we show our results on Kitty dataset sequence 15. Here again, we see the snippets for with and without dynamic objects after applying our method. As seen, the ghosting effect on the left and on the right, the clear point cloud. Next up, we show occupancy octomap superimposed on a point cloud for our dataset. The blue voxels represent the occupancy octomap, and the red points show the dynamic points. We are removing the dynamic object points using the occupancy octomap as a filter on the input point cloud scan, seen in the video. These are some results from our test performed on Kitty dataset. The sequence is from a road category, which represents our use cases perfectly for autonomous driving in urban structured environments. It presents wide highway roads with moving cars or pedestrians. To the best of our knowledge, Kitty only has few loops of driving through the same parts of the map, mostly for loop closure. We have ground truth available for the moving objects for Kitty dataset. The reason for not perfect values is primarily because of having only single loop of data for Kitty. Again, holes on the walls and ground contribute to false positives. This, again, we compare our results with Postica et al. Paper to benchmark our results.